We have an important lesson today. So the title of this lesson is called The Fundamental Theorem of Calculus. So we're going to be connecting the derivatives and integrals today. So it's a really important theorem that we're going to be learning about, and then we're going to be applying it in order to calculate integrals for the first time. Well, we did some calculating in the last lesson, but only for simple curves. So today you're going to be able to calculate the integral of many different functions. Okay, so we're going to start out with this function here that's drawn in pink, y equals f of t. And let's say that this is our function, and we're going to be calculating g of x, which is going to be the integral from 0 to x of f of t dt. So we're going to first write down some values for g of 0, g of 1, g of 2, etc., and then we're going to sketch a rough graph of what this g of x function looks like. Okay, so let's just start doing that. So g of 0 would be the integral, so I'm just copying out what it says g of x is, from 0, and in this case our x value is 0, f of t dt. So the area from 0 to 0, well, that would be 0. G of 1 would be the integral from 0 to 1, f of t dt. And we can calculate that exactly because that is just a triangle, right? So I'm shading that in there. So that would have a height of 2 and a base of 1. Okay, so the value of g of 1 would be 1. G of 2 would be the area from 0 to 2 of f of t dt. So now we're looking at this blue shaded area. So onto my triangle, I have to add on this rectangle. So I had the 1 from the previous area, and then I have a rectangle with an area of 2, so it'd be 3. So the area under the curve from 0 to 2 is 3 exactly. G of 3, so from 0 to 3, I'll zoom out a little bit so we can see everything. There we go. F of t dt is 3. The previous area is already done, plus we're going to just estimate this as not an exact triangle, so I'll put a little squiggly line. But that area of that triangle would be 1 also. So I'll say it's about 4. Okay. G of 4 is the area from 0 to 4 of f of t dt. So now I've got some negative area to add on. So I'll have my 4 that I've already done. I'll use red for negative. The area of that triangle is approximately, well, it's not an exact triangle, so it's approximately 1. So I'll subtract 1. So it's about 3. And lastly, I'm going to subtract another negative rectangle, get g of 5. So 3 minus 1 is approximately 2. Okay, so we're going to plot this function g of x here. So it's the area from 0 to x of my function f of t dt. So at 0, we had 0. At 1, it was 1. At 2, it was 3. At 3, we had a value of 4, and then it was 3, and then 2. Okay, so I'm just going to connect those lines with a curve. Okay, so something like that. All right, so here's what I want you to notice. If I took the derivative of g of x, so the derivative of, consider the derivative of this. So the slope would be positive here. It'd be constant in this region with a slope of 2. Positive here and then negative. The derivative actually looks like that. So the derivative of the area graph is the original graph. So that's what the fundamental theorem of calculus said. So the derivative of the integral is the original function. So the fundamental theorem of calculus is that integrals and derivatives are essentially sort of opposite operations. And that is a really cool thing. So here's what the fundamental theorem of calculus part 1 is. So if f is a continuous function, then, and g of x is defined as the area under the curve from a to x, which is kind of like what we just did up there, then if you take the derivative of g of x, you get the original function f of x. So derivatives kind of cancel out, sort of in a way, area. Another way to think of it is geometry. So if g of x would be the area from a to x of f of t dt here, if you think about g prime of x, it's like how g of x is changing with time, the instantaneous rate of change. So the way that, if you added a little bit on, so the way that the area would be changing is by however high the, by the height of the function, right? So the higher the function, the more the area would change. So that's another way to kind of think about it. So the rate of change in the area depends on the height of the function value at whatever point you're at. So that's another way to think about it. You don't have to memorize this theorem, but you should understand that the derivative kind of cancels out the integral. They're opposites of each other. Okay, so let's just do a quick, easy example. So let's say we have this function. We want to take the integral. G of x is defined as the integral from 0 to x of this function 1 plus t squared, square root of that. So if we took the, oh, I already wrote the answer in here. So the derivative of g of x would just then be the original function. If you're using the variable x, then you would write the function in terms of x. Okay, so that's all that it's saying, is just taking the derivative of the integral gives you the function back. Okay, fundamental theorem of calculus part 2. This is where we're going to be able to calculate integrals today. If we want to find the area under the curve from a to b of f of x, then we need to find something called the antiderivative. And we evaluate that antiderivative at b and at a, and we subtract them. So I'm going to go slowly and show you what that means. I'm going to highlight this word antiderivative. Okay, so I'm going to zoom in. Okay, so let's look at this one. We're looking at the curve x squared, and we want to find the area from 1 to 3. So let me just write this down. Normally I do a whole section on antiderivatives in the previous unit, but because this year is condensed, we're not doing that this year. So I'll go slowly with the antiderivative. So the antiderivative of x squared. So it's like doing the opposite of the derivative. So for a derivative, we would bring the power down and reduce it by 1. For the antiderivative, we do the opposite of that. So we bump the power up and we divide by that power. So here's what an antiderivative is. If I take the derivative of this, I should get this. Let's try it. Let's see. Check. If I take the derivative of this, I should get x squared back. So the 3 would come down. It would cancel out with the 1/3. And then you would get squared, so x squared. Okay, so the antiderivative is like going backwards 1 step. It would be like, yeah, so you want the function that would, when you take its derivative, you get the original function. So I'll let you sit with that for a second. It just takes a lot of practice, but you're kind of doing the opposite of a derivative. So the antiderivative of x squared is 1/3 x cubed, okay? And we want to evaluate that at 3 and 1 and subtract them. The way we write that down notation-wise is like this. We write down the antiderivative, And then we write this bar, and we write a 3 and a 1. So what that bar represents is evaluate it at 3 and 1 and subtract. Okay, it's a short way of saying that. So it'd be 1/3 times 3 cubed minus 1/3 times 1 cubed. Okay, and if you calculate that, you get 26 over 3. Okay, I'm going to show you guys how to check your answers using Desmos. I'm just going to share my full screen here. I'm going to go to Desmos. So if you want to do an integral in Desmos, well, actually, first let's define our function x squared. If you want to do an integral, you can just type int, and it automatically pops up. And we're going to go from 1 to 3, and you can do f of x dx, and it'll just tell you what it is. And if you hit the little fraction button in the side here, it'll tell you as a fraction, or you can get it as a decimal. Okay, so you can check your answers this way, or obviously there's an answer key as well. You can also just type in the function instead of defining f of x first. It'll give you the same answer. Okay. All right, so next one, antiderivative of e to the x. So we're looking for the function that would give e to the x as its derivative. Well, e to the x is an easy one because the derivative of e to the x is just e to the x. So the antiderivative is also e to the x. Because if we check, d by dx of e to the x is just e to the x. Great, that's an easy one. So our answer to this integral, the area under the curve, would be e to the x evaluated at 4 and 0. So e to the 4 minus e to the 0. This is going to be a decimal number because it's irrational. So I'll just round it. About 53.6. Okay. Again, you can check that in Desmos if you want. Okay, let's do cos x. So antiderivative of cos x. So we want the function that will give cos x as its derivative. So that would just be sine x. Okay, so check. If we take the derivative of sine x, we get cos x. So that's the correct antiderivative. So we're going to be evaluating at sine x at pi and 0 and subtracting. So when you use your calculator for this, if you don't already know what sine of pi is and sine of 0 is, if you have not taken pre-calc 12, then you want to make sure you're in radian mode. Okay, I'll just put that under here. If you're not sure how to turn your calculator into radian mode, let me know and I will help you with that. So sine of pi minus sine of 0, it turns out to be 0. Wait, what? How can we have a 0 area under a curve? How does that work? It's not a flat line curve. How do we have 0 area? Let's have a look and see. Let's do cos x. We're going from 0 to pi, right? I'll zoom in here. Look at that curve, right? So we have equal parts above and below the x-axis, so the areas completely cancel out. And so that's why the area is 0. So we can just double check. The answer is 0. Okay. If we were to go from 0 to 2 pi, though, oops. Oh, it's undefined. Oh, right, because I haven't defined it here. There we go. Then it is going to be, oh, it's also going to be 0. Huh. But if I let's say went from 0 to pi over 2, it's going to be a non-zero number. So the area from here to here is exactly 1. So it depends, but it can be 0 if the area above and below the x-axis completely cancels out. Okay, and lastly, Oh, I put this in here. I'm not sure if we've done lns yet, but I will, yeah, we'll add it to our repertoire. Okay, so antiderivative of 1 over x. So the antiderivative of 1 over x, this is not going to be like, there's no bumping up of the power. So this is x to the power of -1. If you bump up the power, it's going to be 0. That doesn't work. Antiderivative is ln x. I can't remember if we've already done ln x examples in class, but if we haven't, there we go. So check. So the derivative of ln x, if we haven't gone over it already, here it is, it's 1 over x. So that's another thing that you should add to your repertoire of derivatives. So the derivative of ln x is 1 over x. So the antiderivative of 1 over x would be ln x. Okay, so this would be ln x evaluated at e and 1. So ln e minus ln 1, which would just be 1. So the area under 1 over x from 1 to e is exactly 1. Okay, that's kind of cool. I think that's cool because you're going from 1 to an irrational number, and the area under a curve as simple as 1 over x can equal an exact number, even though the x value is irrational. I find that cool, but anyways. Okay, so here are your practice questions. I would highly recommend doing the extra practice questions because when I made this assignment up, like I said, in previous years, we've done a whole section on antiderivatives, and so students already had that practice. So I would recommend you do all of these for this lesson, just to practice doing antiderivatives. If you need to see more examples of antiderivatives, I would Google Khan Academy antiderivative, and then they'll show you more examples if you need them. All right, I'll end our video there.